Hi. For today we will be doing numbers. I will talk about the arithmetic of complex numbers, or first how to plot them geometrically. Then I'll talk about a little bit of the arithmetic of complex numbers, its polar representation, and finally, I will talk about some of the and also I will talk about its Euler representation, or also known as the exponential form, and some of the applications of complex numbers of these forms, such as the roots of unity and proving trigonometric identities. All right. So, as you know, a real number line can be all the real numbers can be represented by this number line with 0, 1, 2, -1, -2. In a complex number, we denote I as being equal to the imaginary number as square root of 1. And a complex number denoted as z can be rewritten as a plus b times I, where a and b are both real numbers. So how do we plot complex numbers? Well, there's two things going on. First, there's the imaginary number line, and then there's the real number line going on. So one way to plot complex numbers is by plotting them in this plane, where the horizontal axis is the real number of z, which is a, and the vertical axis is the imaginary number part of z, which is equal to b. I hope you kind of understand how this works out. Basically, the y-axis is the imaginary part of z, and the x-axis is the real part of z. Alright, so let's plot a couple of points. Okay, so let's plot the number z is equal to -3 plus I. Well, the imaginary part of I is 1. The real part of I of this complex number is -3. So the point would go right here. Next, let's plot 3 plus 4i. Well, 3 is the real part of this, which is right here, and the imaginary part is 4, so the point's right here. So let's move on to the polar representation. Which will use trigonometry. Okay, so I will redraw this. any complex number z another way of thinking of a complex point on the complex plane or a complex number z can be equal to the argument or this angle, right, the angle from the x-axis, as well as the radius, which is the distance from the origin. To give an example, let's say this point is actually, and one thing is that to convert from polar coordinates to rectangular coordinates, x and y, we know that x is equal to r times cosine of theta, because cosine is the horizontal part of this, and if we represent this as a right triangle, the x coordinate will be right here, while the y coordinate will be the sine of this, which is the y, or r times the sine of theta will be the y coordinate, or you can just think of it, or the imaginary coordinate. So since a complex number can be represented as z equals x plus iy, notice I'm going to use x and y from now on as the variables to represent the real and imaginary part because of its relations to the Cartesian plane instead of a and b. So z can actually be rewritten as r times cosine of theta plus I times sine theta. Something else that might be helpful. So that's just how you convert from the polar coordinates to rectangular coordinates. To find the radius, what you can do is use the Pythagorean theorem and take the square root of x squared plus y squared. You can take this to find theta. You can take the slope of the line x over y, and we know that the tangent is equal to the slope, so tangent of theta is equal to y over x. You can take the arctangent to find theta. Okay, let's do an example. Let's plot the point where r is equal to 2 and theta is equal to pi over 3 radians. So, to find x, we want to find 2 times the cosine of pi over 3. And we know that the cosine of 60 degrees is just 1/2, so it should be 2 times 1/2, which is equal to 1. And then we want to find y, which is 2 times the sine of 2 times square root of 3 over 2, which is the sine of pi over 3, which is just square root 3. That's about 1.7. I memorized that square root of 3 is about 1.7. So I'm just going to write this I'm just going to write the x part as some point between 1 and 2 that's closer to 2. Just be right here. The drawing of the coordinate plane is not to scale. Alright, so why is this important? Well, something that we could do with complex or the polar representations of complex numbers can do is help us multiply. So is to help us multiply complex numbers, because alright, well, it can help us rewrite it in this form called Euler form, which is e to the I, which allows a complex number to be written as r, which is just the radius from the origin, times e to the I theta. E is the Euler's constant, which is the limit as x approaches infinity. Let's do as n approaches infinity of 1 plus 1 over n to the nth power. If you know calculus, then I will I'll briefly explain how this formula is derived. So, if you know the Taylor representation of e to the x, and plug in I as a multiple of x, Taylor series would be the same as a cosine of x plus I times the sine of x. Right. And of course that gives us our polar representation of a complex number. Let's look at the geometry of these complex numbers and see what happens if we multiply them together. So I'm guessing you already know how to add complex numbers pretty well and what that looks like. But to multiply complex numbers is a little bit more complicated. So let's say we have one complex number, z1, and another one around here that's z2. So z2 can be rewritten as the radius 2 times e to the I theta 2. While z1 can be written as radius 1 times e to the I theta 1. We multiply these together, we end up with magnitudes being multiplied together, and then since e is to the I theta power, multiplying these together will actually just be e to I times the sum of the angles. So geometrically what that looks like is we want to add these angles together. So I'm guessing it's going to be somewhere up here. Multiplying these radii together will give us a really long magnitude that's somewhere up here. So let's look at the exponentiation of a complex number, z. Let's say we want to take z. We already know that z can be equal to r times e to the I theta. But what if we want to take z to the nth power, which is an exponentiation of a complex number? Well, all the radii will be multiplied together n times. So the magnitude will be r to the n. This will be multiplied by e to the I times n theta. Since theta is being added to itself n times. This leads us to de Moivre's theorem. So, if we have a polar coordinate r and theta, this is another representation of in polar form, except we just use a coordinate system, and we take this to the power of p over q. This would just be the same thing as r to the p over q p theta over q plus 2 pi over q, k over q, where k is some integer. Because when we add 2 pi to a complex number, it will be multiplied. If we add 2 pi to the angle of a complex number, also known as the argument, it will just be the same thing, just one more times around the circle with the radius of the magnitude. So let me do an example of this. Let's find all the cube roots of. Let me find all the cube roots of z equals 4 plus 4 square root of 3i. So first, I want to find the convert this to the Euler form. So I know that the magnitude of z is the same thing as square root of 16 plus 48, which is equal to 8. So this is 8 times 1/2 plus square root of 3 over 2i. And this is the same thing as cosine of theta, cosine of theta. And this is the same thing as sine of theta. Just recognizing our trigonometry, our special angles in trigonometry. We know that theta is actually just 60 degrees. Oh, wait. Sorry. That's the wrong sign. So it's the same thing as 8 times e to the 60 degrees, I times 60 degrees. And taking the cube root of this will be the same thing as 2 times e to the 20 I. And oh wait, something that might be helpful is to write the argument as, or angle as I times 60 degrees plus 360 degrees times a constant. And dividing this by 3 will be 20i plus 20ik. So there will be 3 values. Depending on what number k is, there will be 3 different angles that can work. Okay, so how can we apply this concept? Well, one thing we can do is prove the double sum identities of trigonometric functions. So I claim that cosine of x plus y, which are two angles, is the same thing as cosine x times cosine y plus, oh, yeah, this is right. Oh, it's actually minus sine x sine times sine y. So cosine of x plus y, what we can do is find e to the I to the x plus y. Just cosine of x plus y plus I sine of x plus y. This is the same thing as e to the ix times e to the iy, which is just cosine of x plus I sine of y, or I sine of x times cosine y plus I sine y. And after using the distribute, after expanding this, the factors, I will end up with cosine y times cosine x. In the real part, I will end up with cosine y, cosine x, minus sine x and sine y. Remember, when we multiply I and I together, I squared is just -1. And then we get something, and in the imaginary part, we get I times cosine x sine y plus sine x cosine y. And equating the real, and here we can equate the real parts together to find the solution. And we can also find an expression, a way to prove the sum of angles for the function sine as well. Lastly, let's look at the roots of unity. So this is just the nth root of 1. So as you know, 1 can be equal to e to the I times 2 pi k in radians. I to the 1 over nth, however, will be, which is the nth root of 1, will be equal to e to the I times 2 pi k over n. And if we rewrite this on a complex number plane with a circle of radius 1, since if this is a complex number, its magnitude will be 1. This will actually show this will actually divide the circle into n sections, like this, because the first one will just be, if k is equal to 1, it will just be e to the 2 pi over n. And if k is equal to 2, it will be e to the 2 pi over n times 2. And it will keep going.